rapidly varied flow has the following characteristics or features. 1. The curvature of the flow is such that the pressure distribution is not hydrostatic. 2. The flow variation takes place within a relatively short reach. 3. The frictional force is small compared to the other forces acting. 4. The physical characteristics of the flow are fixed by the rigid boundary geometry. 5. The velocity distribution coefficients are much greater than 1 and cannot be determined accurately. 6. Separation zones, eddies, and rollers tend to complicate the flow pattern, which becomes distinctly three-dimensional. A satisfactory solution for rapidly varied flow does not exist. Empirical solutions are used in the absence of theory. The sharp-crested weir is the simplest form of overflow spillway. The shape of the flow nap over a sharp-crested weir can be interpreted by the principle of the projectile. It is assumed that the horizontal velocity component is constant. Thus, the only force acting on the nap is gravity. Kinematics leads to a parabolic equation for the nap surface. With the coefficients the shape of the flow nap over a sharp-crested weir is useful in the design of overflow spillways. The broad-crested weir equation is in which Q sub D is the design discharge, C sub D is the discharge coefficient, L is the weir or spillway length, and H sub D is the design head above the crest of the weir, excluding the velocity head. Theoretical values of C sub D, assuming critical flow in the vicinity of the weir crest, are 1.7 for SI units and 3.09 for US customary units. Actual values vary with the shape of the weir crest and the roughness of the boundary, and they are typically less than the theoretical value. Values varying between 80 to 85% of the theoretical value are in common use. Efforts to increase weir discharge while keeping the head constant have led to the concept of labyrinth spillway. A labyrinth spillway increases the effective length of the spillway without actually taking any more physical length, as shown in this example. In practice, the labyrinth spillway works for a limited range of heads. For very large heads, the labyrinth becomes submerged, and the effective length of the spillway reverts back to the original length. An OG spillway is an overflow weir whose cross-sectional shape matches the underside of the nap at its upper extremity. The U.S. Army Corps of Engineers has developed a series of OG spillway sections collectively referred to as West standard spillway shapes. The equation for the West spillway shape is X and Y are the coordinates of the crest profile, with the origin at the spillway crest. H sub D is the design head, excluding the velocity head. K and N are parameters that depend on the slope of the upstream face, as shown here. For West shapes, the discharge of the overflow spillway is where H sub D is the total head above the spillway crest, including the approach velocity. Tests have shown that the effect of the approach velocity is negligible when the ratio of spillway height to design head is greater than 1.33. In this case, the discharge coefficient is 4.03 in US customary units. This value is 30% greater than the theoretical value for a broad-crested weir, 3.09, which implies that the West spillway shape is very effective in passing the flow. For low spillways, the effect of the approach velocity is to reduce the discharge coefficient below the value 4.03. Determine the crest elevation of a West spillway section having a vertical upstream face with the following hydraulic and geometric data. The discharge Q is solving for total head above the spillway crest. The approach velocity is the design discharge divided by the flow area. The velocity head is the design head is the spillway height is the ratio of spillway height to design head is Therefore, this is a high overflow spillway, and the assumption of discharge coefficient equal to 4.03 was correct. The spillway crest elevation is the equation for the spillway shape is for a vertical spillway face, K equal to 2 and n equal to 1.85. With the design head h sub d equal to 2.858, the equation for the spillway shape is to calculate the coordinates of the end of the profile on the downstream face of the spillway at the point of tangency. The derivative is solving for the x coordinate of the end of the profile x sub o at the point of tangency. Replacing x sub o in the equation for spillway shape, the spillway profile is designed for one head, the design head. For heads lower than the design head, the pressure on the spillway is above atmospheric and lower than hydrostatic. For heads higher than the design head, the pressure on the spillway is below atmospheric, and this may lead to flow separation. The design head may be exceeded by up to 50%. Beyond that, harmful cavitation may develop. The design head h sub d excludes the approach velocity. The total head h sub capital D includes the approach velocity. The spillway rating is based on the theoretical broad-crested weir equation, which assumes critical flow in the vicinity of the weir crest. The actual design discharge is in which C sub capital D is the discharge coefficient applicable to the design discharge, varying with relative spillway height in the range 0.385 to 0.492 as shown here. The higher values apply for higher spillways. Note that the actual discharge coefficient could be up to 28% higher than the theoretical value, depending on the height of the spillway. For any head, the spillway rating is where C is a function of H. The spillway rating is also where the relative discharge coefficient C over C sub capital D is a function of relative head H over H sub capital D as shown here. A step-by-step procedure to develop a spillway rating is the following. 1. Develop a suitable array of heads H above spillway crest from 0 up to 50% in excess of the design head H sub capital D. 2. For each head H, calculate the relative head H over H sub capital D. 3. For each relative head H over H sub capital D, enter this figure to determine the relative discharge coefficient C over C sub capital D. 4. Given the spillway height P, calculate the relative spillway height P over H sub D and enter this figure to determine the design discharge coefficient C sub D. 5. For each head H, calculate the actual discharge coefficient C equal C over C sub capital D times C sub capital D. 6. For each head H, calculate the corresponding discharge Q. As shown here, the discharge coefficient increases with the operating head. Therefore, a spillway crest becomes more efficient at heads that exceed the designed head. However, this apparent advantage comes at the expense of increasing subatmospheric pressures on the spillway, which may lead to cavitation. As an example, assume the following spillway data. The results of the spillway rating are summarized in this table. The results can be confirmed by running onlinecalc.sdsu.edu/onlineograting.php.